Thanks a lot for inviting me. It's really a pleasure to talk to you about some of our recent work at the University of Vienna. And it's also really an honor to present our work with you in Cambridge, since so much of this research topic has been initiated and developed there. So this is a really short overview of the talk. So I'll talk about our flavor, let's say, of machine learned potentials that we do in VASP. And I'll talk about some applications studying thermodynamic properties, in particular for one material, zirconia. So I'll talk about phase transitions and thermal conductivity. And I'll talk about a scheme, a delta machine learning scheme to train force fields with beyond DFT accuracy. And if I have enough time, I'll also spend a couple of minutes talking about another application that might be interesting for some of you, which is the study of antiphase domain boundaries in strontium titanate. This work, of course, was not just done by me. I'd like to thank all the collaborators, in particular Ferenc Kassai and Rioska Ginucci, who worked a lot on the implementation of machine learning force fields in VASP, Peitao Liu, who worked a lot on the delta machine learning, and of course, Georg Kresse. So the motivations and background of the work are very, very broad and general. But of course, we all agree that a dream of a lot of physicists and material scientists is to be able to predict thermodynamic properties with really good accuracy. So we would like to ideally be able to predict free energies, phase transitions of materials, and thermal properties like thermal expansions, conductivity, and diffusivity. And these are all properties that require really long time and size scales to really be able to calculate them accurately. And also the properties that involve anharmonicity, and it is pretty hard to capture anharmonic properties with enough accuracy, as we will see later. Now, you're probably all familiar with this sort of schemes where on one side you have a first principles method, which are ideally very accurate. Of course, I'm putting everything here in the same box, DFT and higher level methods, but they're of course really slow. And then on the other side, we have the traditional force fields, which are really fast, but often inaccurate. And particularly they have problems when a larger phase space is explored, and also they particularly have problems with anharmonic properties. And then in the last few years, the area of machine learned potentials have emerged, which combines the desired accuracy and speed. Of course, not as fast as empirical force fields, although some groups are getting there. And this plot here is actually starting to be a little bit out of date. It shows you errors versus computational costs for different types of machine learned potentials, showing you really what can be achieved. And again, as I was saying, this is almost a little bit out of date, meaning that improvements happen pretty much every month in this area of work. And this is an application that I really like, taken from this work. It shows the kind of famous silicon 111 surface, the 7x7 surface reconstruction, which is predicted by DFT, but standard force fields are not able to predict this. They just show the 1x1 as the most stable surface. But the subgap force field is able to reproduce the DFT result. And for example, when experimentalists see this sort of result, they immediately trust force fields. They are somewhat skeptical, often of various theoretical approaches, but they get convinced by this. The idea behind machine learned interatomic potentials, I'm sure most of you are familiar with, so I don't need to explain too much. But the idea is that we need to construct a reference database to train our potential. we need to represent the atomic environments using descriptors, and then we need to solve the regression problem. And this area of research is now fairly mature, although challenges are still open, and I can refer you to these really nice reviews here if you want to learn more. Now, I'll just spend one slide to tell you what we do. Again, what I was saying, our flavor or machine learned potentials. So what we do to learn the potential energy surface is to, of course, first map the local environments onto a set of descriptors that are based on the 2 and 3 body distribution functions. Our descriptors are very similar to the SOAP ones. And the potential energy is then expressed as a summation of atomic energies, which are expressed as nonlinear combinations of kernel functions that measure essentially the similarity between the atomic environment around each atom's I and certain other reference atomic environments. Now, one then collects all the ab initio data, so for the total energy, forces, and stresses into this quantity Y. You set up the design matrix consisting of the various kernels and kernel derivatives to represent energies, forces, and stresses. And then what you have to do is to solve the regression problem to find the coefficients. And this can be done, for example, using Bayesian linear regression to optimize some regularization parameters, or simply using singular value decompositions even without any regularization. We train our force fields on the fly during molecular dynamics. This is a scheme that we found is very robust and general, and it is increasingly being adopted in the community, not necessarily, of course, using VASP, but this scheme is now integrated and distributed with VASP. And so how it works, very briefly, is that you start reading in an existing force field, of course, if you have it available, and you use it to both predict the potential energy surface and the associated Bayesian uncertainty. If this uncertainty is too large, then you go back and do a first principles calculation from which you proceed selecting the relevant data and retraining the force field. And you can continue from here doing your molecular dynamic steps. Now, using this scheme, we decided to work on zirconia. The reason for picking zirconia are multiple. Here, I just want to highlight that, of course, it's a material that is very important from a technological point of view, and it's also a perfect example of a strongly anharmonic solid. It has a fairly complex phase diagram. At 0 pressure, you go from a monoclinic structure, here at low temperature, that transforms into a tetragonal structure around 1400 Kelvin, and then a fairly large temperature around 2500 Kelvin, it becomes cubic. Zirconia is used, for example, in solid oxide fuel cells, or cubic stabilized zirconia is for example, used as a fake diamond. Now, these are just some brief details of our training and validation of force field. You see, using this on-the-fly training scheme, you're able to train a very accurate force field using only less than 600 DFT calculations at the PB-SOL level, with each calculation performed with pretty strict convergence parameters. And we go up to temperatures of about 2800 Kelvin. So you see here the errors in energies, forces, and stress tensors compared to the DFT data. You see in this region here, the errors in energies are larger, and that is because these energies correspond to the very high temperature cubic phase. So of course, you have to expect larger errors when temperature goes up. These are the root mean square errors comparing regularized and non-regularized solution. And you see that even without regularization, you don't incur overfitting. So the training and test errors are very similar. More interestingly, these are the phonon dispersions of the cubic structure. You see here there are these negative, or let's say imaginary phonons, and this soft phonon at X is very crucial for the cubic to tetragonal transition. It drives this transition here. So capturing it even at the harmonic level is very, very important in order to then quantitatively capture this phase transition. And these are the errors in the phonon calculations more quantitatively. Now, looking at the phase transitions, we first did a slow heating and cooling of the material. So you see that the tetragonal to cubic transition doesn't show any hysteresis, but instead the monoclinic to tetragonal transition is discontinuous. So it's a first order Martin-Segy transition. And when we cool the system, it actually stays tetragonal, so it is non-reversible. These are the lattice parameters versus temperature. You see they're in really nice agreement with experiment. This is the monoclinic angle. However, if we want to quantitatively look at the phase transition temperature, we need to do better than a simple molecular dynamic, let's say a straightforward molecular dynamic run. We need to look at free energy differences as done here. Now, free energy differences are traditionally often calculated in the quasi-harmonic approximation, where the anharmonicity is taken into account by calculating essentially the free energy of the system as a function of temperature and volume, where the phonons are taken as dependent on the volume, and then you minimize the free energy to get the Gibbs free energy at each temperature. So to get a fully anharmonic free energy for each phase, the monoclinic and tetragonal phase, we use thermodynamic integration, where we integrate from the quasi-harmonic free energy at low temperature. And this is the free energy difference that we obtain. And you see that that gives a transition temperature in better agreement with experiment, and particularly you show you look at the difference between the predictions from a quasi-harmonic theory and a fully anharmonic theory. Instead, for the tetragonal to cubic transition, since it's largely second order, you can simply look at, for example, the tetragonal parameter here, plotted versus temperature, and you obtain here the transition temperature. Now, of course, this is done training a force field at the level of PB Sol, which is pretty accurate, but of course, it will only be as accurate as the underlying first principle theory uses. So in this case, DFT with the PB Sol exchange correlation functional. Now, what we would like to do ideally is to be able to train force fields that have even beyond DFT accuracy. And for that, we use the delta machine learning. Now, the delta machine learning scheme is not new in itself. It was suggested, for example, by the group of von Linienfeld a few years ago, and then it's been used in a number of works recently. The ansatz, the underlying idea is that the DFT calculations capture the most important features of the potential energy surfaces. And then you can learn just the deviations between these DFT calculations and the high-level calculations, which are expected to be smoother and easier to learn. So you can learn this difference using a smaller number of configurations with smaller unit cells, and essentially also using fewer descriptors. Now, what we wanted to come up with was a fairly robust scheme to learn the random phase approximation. Now, the random phase approximation is a many-body theory to describe electronic correlations. It's, of course, much more expensive than DFT. The advantages is that the RPA in VASP has been implemented recently using a cubic system size scaling, so it is more computationally affordable. And also there's been a nice theoretical development in order to calculate forces directly from the RPA, so not using finite differences, which would be very time consuming for each atom. And then the stress tensor instead can be computed fairly quickly via finite differences. So exploiting all this, this is what we did essentially. This is our scheme for delta machine learning, a force field. So not just, let's say, correcting energies, but training a force field that can give stable molecular dynamics trajectories. So essentially you start from your initial data set that you use to train your original, let's say, low-level force field. And then you do another on-the-fly active learning. With this, you extract a new data set that you can compress so that you have fewer configurations. And also, I didn't mention, this is done using smaller unit cells. You can then perform also your expensive high-level calculation on this smaller data set. And then you can calculate delta, the difference between your high-level method and low-level method calculations. You use these calculations in order to train a force field that we call MLFF delta. And you use this MLFF delta in order to correct your initial data set. And with this, let's say, corrected data set, you can train a force field that supposedly should have the same accuracy as training a force field directly on your high-level calculations, which is unaffordable. Now, to test the scheme, we did it on zirconia, since we had worked on it already. And as a low-level method, we used PBE, and as a high-level method, we used SCAN, which is, of course, not as expensive, but we did it for testing purposes, and the random phase approximation as expected, of course. So our T1 dataset is the original one that I used before. And our reduced dataset for delta learning is this one here. And actually, we later figured out with more careful study that we could have used even fewer structures, even half of these structures. These are some tests for our delta learning strategy using SCAN. And you see that comparing the root mean square errors of a force field trained directly on SCAN or a force field trained using the delta learning scheme, these root mean square errors are pretty much the same, and the estimations that you get with these two force fields are pretty much identical. Then training an RPA force field, we get these test errors here. Of course, these are calculated using smaller cells, and you see they are comparable between PBE and RPA for these test sets. It is always very instructive to test on phonon dispersions. These are the phonon dispersions for all three phases, and you have the monoclinic tetragonal and cubic phase, and here in gray are the underlying PBE calculations, and in red the RPA results. The blue dots are direct RPA calculations. So you see they agree quite well with the force field estimations. So we used the SCAN and RPA force fields to do again these calculations that I showed you before to study the phase transitions or zirconia. So these are similar plots where these are for heating and cooling runs, and these are the free energy differences and the tetragonal ratio to get different phase transitions. And by doing this, we obtain these updated estimations. You see that now SCAN does better than PBSOL, and the RPA does even better, although SCAN is already in very nice agreement with experiment. So, of course, this application was mainly for testing purpose in the strategy, and then we are now working on using this for more, let's say, interesting and complex systems. Another application that I wanted to talk about was thermal conductivity, which I know is also very dear to some of you in the audience. Now, the thermal conductivity kappa is related to the heat flux and the temperature gradient in the material by the Fourier law. Now, looking at phonons at the heat carriers, one can study it, calculate the thermal conductivity using a reciprocal space representation, where you solve generally the linearized Boltzmann transport equation. This is in the relaxation time approximation. So essentially, you look at the phonon-phonon scattering that gives you the phonon lifetime tau. These are the phonon group velocities, and this is the heat capacity. And this theory has been used, of course, countless times in the literature. However, it can only describe crystals with not too strong anharmonicity, and so also at not too high temperatures. Instead, if we look at the real space representation, essentially doing molecular dynamics calculations, either in a non-equilibrium or equilibrium setup, you can capture much stronger anharmonicities, and you can capture not just crystalline solids, but also amorphous or solids or liquids. Here we focus on the Green Kubo theory. So in the Green Kubo theory, the thermal conductivity is given by the integral of the heat flux autocorrelation here. And what is interesting is that, of course, to converge this quantity, you need pretty large supercells and long simulation times, which make ab initio calculations of Green Kubo thermal conductivity extremely hard. But actually, until very few years ago, people were thinking that ab initio Green Kubo calculations were fundamentally impossible because the heat flux was ill-defined. This is now shown that it's not the case, but still these calculations from first principles are still computationally very demanding or unfeasible. When you have many body potential, the formulation for the heat flux is pretty simple. It's given here. And this expression is general, it's valid for any many body potential. The caveat is that, you can express the heat flux also in this way. So essentially, you can recast this term using an atomic stress tensor definition. However, many calculations rely on lamps, and the atomic stress calculated in lamps was correct only for two body potentials. This problem was pointed out very recently, and it was fixed for many body potentials, such as angled dihedral and improper styles. But for other many body potentials, such as Tersov or machine learned potentials and so on, this is not fixed in lamps. So the reason why I'm mentioning this is that thermal conductivity calculations using machine learned force fields are coming up in the literature, but one needs to be careful when these are done not using a custom implementation, but using lamps. So I'm showing quickly our results. This is the heat flux autocorrelation function in zirconia for different temperatures. You see, it decays pretty quickly. This scale is picoseconds, but still to converge it, you need very long trajectories, and you need averaging over various trajectories. And the integral gives the thermal conductivity, and these are the results. In red are results for the thermal conductivity versus temperature. And you see they are in a pretty nice agreement with experiment, although they are a little bit underestimated. But the temperature dependence is in good agreement, whereas empirical force field calculations shown here in orange show a discontinuity at the phase transition and not the expected temperature dependence. Now, do I have a couple more minutes, or should I stop here?
Yeah, you can finish in a couple of minutes.
Okay, sure. I just want to then really quickly tell you something about Strontium Titanate, so a completely different application. I'll kind of maybe skip on the introduction of Strontium Titanate. You'll know it's kind of like the silicon of perovskite oxide, right? It's super interesting. It got this antiferrodistortive and ferroelectric instability that are shown here in the phonon dispersions. This is the ferroelectric instability, and this is the antiferrodistortive one in the cubic phase. So we trained a force field for Strontium Titanate. I'll spare you all the details. But the reason why we wanted to train a force field for Strontium Titanate was that we wanted to study domain walls. Now, domain walls are essentially the separation between different domains in a material. So, for example, in strontium titanate, you have these antiphase domain boundaries below in the low temperature tetragonal phase. You see here, this is an example of a domain boundary where the boundary is perpendicular to the tetragonal axis, to the z-axis, and here it is parallel. So these domain walls here are the more interesting ones because the thickness of this domain wall can be pretty large, and they exhibit more interesting properties. The reason why these domain walls are interesting to study is that they can really be exploited for nanoelectronics applications. So we validated our calculations versus ab initio calculations in fairly small cells, and then we used the larger cells that can appropriately describe these domain walls. And what we found is that essentially this is the primary order parameter, which switches sign at the domain boundary. And this is the secondary order parameter that develops as well. This is called the nail type domain wall. And this is the pressure dependence of the domain wall order parameter. So you see the domain wall becomes thinner with increasing pressure, and this secondary order parameter also decreases in amplitude. And more in detail, this shows you the pressure dependence of the domain wall thickness. I will spare you all the details, but what I wanted to highlight is that we could calculate the polarization of the domain wall. So you know, strontium titanate is not ferroelectric, but a non-zero polarization arises in the domain wall. And also a very interesting result that we had was that we recovered very nice agreement with phenomenological Landau-Ginzburg-Devonshire theory that was traditionally used to study these systems. So I think I should maybe really stop here. If you're more interested in this, of course, you can ask more questions about this final topic. But maybe I'll just leave here the conclusions and all the acknowledgments. And I'm happy to get questions.